Los Alamos, 2001. Three physicists proved quantum computing with light was theoretically possible, using only mirrors and beam splitters. Their gates worked roughly 6% of the time. Scaling meant stacking failure on failure until computation drowned in its own noise. Photons kept vanishing mid-calculation, silently corrupting results nobody could catch. One key architectural insight: encode every qubit across two parallel waveguides. If a photon vanishes, detectors register nothing. The error announces itself rather than hiding. Theory suggests error-correcting codes could tolerate that honest failure at roughly 25%, far higher than the roughly 1% threshold for silent errors. Those numbers come from idealized models. Practical ceilings sit lower, but the gap remains significant. Simultaneously, researchers were slicing lithium neobate, a mineral first cataloged in 1836, drafted into fiber optic cables in the 1980s, into films thinner than a wavelength of light. Nanofabrication work on this material showed single photons guided for centimeters with propagation losses below 0.1 decibels per centimeter, and under 0.03 in leading lab demonstrations. PsiQuantum's February 2025 Nature paper, 145 citations in 14 months, showed that per-component error rates required for a fault-tolerant photonic architecture are now within reach of standard semiconductor fabrication processes. The bottleneck has shifted from physics toward foundry capacity. Fewer than 6 fabs worldwide can produce the thin-film lithium neobate wafers this technology demands, a supply chain concentration that could determine which nations lead. The potential applications are significant: drug simulations where failures dominate clinical trials, and encryption protecting financial records worldwide. Though realizing either depends on scaling challenges not yet solved. The catch is real. This remains at lab-validated subsystem stage, not a working logical qubit. PsiQuantum targets fault-tolerant machines in the early 2030s, credible only if TFLN supply scales and detector and source performance cross key remaining thresholds. 3 things to